In this video, we will be providing an end-to-end explanation of the support vector machine. Let's go over the use case of SVMs. The main use is binary classification, and this can be generalized to multi-class classification using multiple classifiers. The key properties of the SVM which differentiate it from other classification algorithms such as logistic regression are the concept of maximum margin, and the application of kernel functions. The problem that the support vector machine solves can be stated as follows. Given a set of data points xi, represented as n-dimensional real vectors, and their corresponding positive/negative classification, yi, find a hyperplane which most effectively partitions the data into the positive and negative components. Recall that a hyperplane is defined by its normal vector w, and its intercept term b. Further, a hyperplane can be thought of as partitioning the base space into two regions, and these regions are the set of points for which the expression w.x plus b is positive or negative. Note that such a hyperplane may not exist, in which case the data is not linearly separable. We will discuss how the SVM algorithm can deal with this situation later, but for now assume that the data is linearly separable. Recall the formula for the distance between a hyperplane and an arbitrary point. We can define the margin of a particular hyperplane to be the closest distance of any one data point from the hyperplane. For mathematical convenience, we can scale our intercept term to get a simpler expression for the distance. Using this modified definition, we will always have that the absolute value of w.xi plus b is greater than or equal to the margin m times the norm of w. Once again, through scaling, we can get that the absolute value of w.xi plus b is greater than or equal to 1. By our definition of yi, the absolute value of w.xi plus b is equal to yi times the quantity w.xi plus b. Support vectors are the data points xi such that the absolute value of w.xi plus b is equal to 1. Other data points don't contribute to the margin of a particular hyperplane. In this way, we are only constrained when the absolute value of w.xi plus b is equal to 1. Recall that we want the maximum margin. In other words, given all choices of hyperplanes, we want the one which gives the largest minimal distance. By performing the relevant algebra, we see that our optimization objective is equivalent to minimizing 1/2 times the norm of w squared. To solve this minimization problem, we will use Lagrange multipliers. Recall the methodology of Lagrange multipliers. If we want to minimize an objective function f with respect to constraints g sub I, then we take the gradient of the Lagrangian and set it identically to 0. Applying this to our case and performing the relevant calculus and algebra, we reduce our Lagrangian to be just in terms of the multipliers. We can then optimize our solution using gradient descent. Once we have optimized our solution, we can find the parameters for our hyperplane. The decision rule is the same as before. We take the inner product with the vector w, add the intercept term and take the sign of that value. Let's introduce the idea of kernel functions. The motivation is that sometimes the input data is not linearly separable, and we would like to achieve linear separability by mapping those input vectors to a higher dimensional space. The key observation is that the Lagrangian only depends on the inner product of the input vectors xi, and if we were to map our input vectors to a higher dimensional space using a map phi, our Lagrangian is still in terms of the inner product of the vectors. So if we have a function which efficiently computes the inner product phi xi dot phi xj, we can efficiently compute the decision boundary of our input data in a higher dimensional space. This is precisely what a kernel function does, and only a few modifications to the previous approach are needed. Note that a decision rule uses the kernel function instead of the standard dot product, which is referred to as the linear kernel. Suppose we are okay with the data not being classified with 100% accuracy. This is the motivation of a soft margin classifier. The modification to be made with a soft margin classifier is that we introduce slack variables cusI, along with a hyperparameter c. The interpretation of c is that if c is large, we will not be okay with misclassification, and if c is small, we will be. Going through the Lagrange multiplier approach, we will have a Lagrangian in terms of lambda and cos. We can then perform gradient descent to optimize for lambda and cos. Once W and B are found, the decision rule computation remains the same. If you found this content useful, you should consider algorithmspath.com. You can use the promo code SupportVectorMachine for a discount. Thanks for watching.